on to bepicolombo, mission to the inferno. Bepi is not one of the better known ESA missions, but it's an absolutely fascinating one. Now, of course, Bepi is all about Mercury, and Mercury is one of the less explored planets of the solar system. It's small. It's never more than 27 degrees from the sun. In the UK, April, May, you can see it. When I was living in Bristol as a kid, you know, I could usually follow it for 3 weeks after sunset in April and May. Now, with all the light pollution and the building that's been done in my village, I don't think I'd be able to. But this is an image I actually took of Mercury during lockdown last year, because we were allowed out for an hour in each evening for exercise. And when I went out for exercise, usually with my daughter, I had my camera with me. And if there was something interesting to see, I tried to take photographs of it, much to the frustration of my daughter sometimes. But and there is Mercury setting alongside Venus. And of course, it was known to the ancients. They called it Mercury for the messenger of the gods because it moves so swiftly in the sky. And they were not actually sure, in fact, if it was one planet or two. They had the same problem with Venus. And there's an urban legend that Nicholas Copernicus never saw the planet. He lived in Poland, close to the Vistula, and the legend is that the mists rising from the Vistula always blocked his horizon. Now, we know this is an urban legend because for 7 years he was in northern Italy at different universities, and certainly he would have had clear skies. He would have seen Mercury there. But it's one of these lovely, lovely legends. People who live in built-up areas probably never do see Mercury because it's so low down. After sunset, it's very, very difficult to see it. I can't easily see it from the house because it's hidden behind the rooftops in front. I have to go outside, find somewhere with a nice clear horizon to be able to see it. And Mercury is, of course, very small, and at times is only 3 arc seconds in diameter. So I'm going to put on this video. This is a video taken by an American astronomer with a 12-inch Dobson, if I can find the cursor. There it is. And I guess the poor guy must have been observing in a roaring gale, but it does give you an idea of the sort of problems you got with Mercury. You can't see much. Tiny disk. Sometimes you can see the phase. Now I'm going to stop it because the music's a bit, but there's really not much more to see with Mercury. It's said to be the only planet that can twinkle because when it's at full phase, so low down, the diameter's so small, it genuinely can twinkle. Now, I had this problem in practice. Right, finally, it doesn't like me trying to change slides when I stop that video. Really, we see very little. Now, these images should be familiar to Guy because he used them in TA last year. This is from Paul Abel. These are a couple of images of Mercury taken during May as the phase was reducing. And apart from some very dim shadings, you really can't see very much on Mercury. And if somebody like Paul Abel can't see detail, then a person like me, who is not a fantastic planetary observer, I would have no chance whatsoever. However, there are people like the great Greek astronomer Antoniadi, who was lucky enough to work in the French observatories, Pic du Midi, Meudon, very good skies, excellent large instrument. In the 30s, he drew maps of Mercury, even of the satellites of Jupiter. And this was the IAU's approved map of Mercury based on Antoniadi's drawings. He was absolutely convinced that Mercury always kept the same side towards the sun. In fact, he was wrong about that. We know that Mercury spins every 58.5 days, and its orbital period is 88 days. But it turns out that there's an orbit lock, that it spins 3 times for every twice it goes around the sun. So when it's best placed for observation, it's always pointing the same side towards the Earth. And so it's not surprising that he thought that the features on the surface didn't change. And when Mariner 10 finally made its 3 flybys back in 74 and 75, it showed exactly what we expected. Tortured, cratered landscape. The one big surprise is that there were none of the big lava plains that you see on the moon. In fact, there is only one significant lava plain on the moon. It's called the Calores Basin. And here, just for comparison, you show it alongside Mare Imbrium on the moon. And you can see the Calores Basin on Mercury. This thing here, it's not very flat. It's heavily cratered, cracked. There are all kinds of wrinkle ridges in it. It's substantially larger than Mare Imbrium. Calores Basin is an impact formation on Mercury, but it's the only significant one. And in fact, on most Mercury photographs, you would have quite a job to pick out the Calores Basin. It doesn't stand out very much. It's not like the Imbrium Basin. It's not filled with dark lava. At full illumination, you really have great difficulty picking it out. And here you've got Antoniadi's map compared to one of the best Mercury mosaics from the Mariner 10 mission. When people looked at these Mariner 10 images, they thought Antoniadi's map was probably just illusory. However, Antoniadi was a clever chap. He was using big telescopes. And so people tried a test. They took the Mercury maps and they defocused them and they blurred out the detail. And when they did so, they had quite a surprise, because you start to see that there are features that you can identify. You've got a sort of circular bright area here with a dark spot in it. And you do see an albedo feature in the Mariner images with a dark spot. There's a darker area here to the left, and you do see the darker feature. And it turns out that it does look as if most of the features that Antoniadi thought that he could detect on Mercury, you can actually detect as very faint contrast features, albedo features on Mercury, when you completely degrade the Mariner images. So they weren't completely illusory, although there are some details. This one, Neptune Vallis, the Valley of Neptune, I think he only saw that twice in all his observations of Mercury. So that one probably was a little bit optimistic. Now, why are scientists so interested in studying a searing, barren ball of rock? Mercury is at about 430 degrees centigrade, so that's hotter than the surface of Venus. Put your Christmas turkey on the surface of Mercury, and it would be done to a crisp, probably a little bit overdone. Guy, don't suggest to Anne that she uses Mercury, teleports the turkey to Mercury to get it done quickly. it wouldn't come out too well. But Mercury does have one big surprise. And we've known for about 50 years that the poles of Mercury reflect radar very strongly. This Mercury image is from Goldstone, and you can see some patches here that are relatively good radar reflectors. But here, right at the North Pole, there is something that really reflects radar very, very strongly indeed. And this is water ice. That was a big surprise. It was first discovered, I think, in 1973. There were the first indications that there was ice at the poles of Mercury. Now, how do you get ice on a planet where you have an atmosphere that mainly consists of metal vapor? Because at 430 degrees centigrade, which is the temperature subsolar point, so the point where the sun's in the zenith, on the equator, there's oxygen in the atmosphere. It's a very, very tenuous atmosphere, but have a look at some of the other ingredients. Almost 30% of the atmosphere is sodium. 0.5% is potassium, and there are traces of other heavy metals in the atmosphere as well. Sodium is a metal that melts and vaporizes at quite low temperature. So on the surface of Mercury, sodium is going to be evaporating very, very rapidly. And in fact, the source of a lot of the atmosphere is minerals that get broken up by the bombardment by solar radiation. And part of it is captured from the solar wind, like the hydrogen and the helium. Those are mostly captured from the solar wind temporarily, rather like the lunar atmosphere. In fact, there are some interesting parallels between the lunar atmosphere and the Mercurian atmosphere. Mercury has the most tenuous atmosphere of any planet. It's far more tenuous even than the atmosphere of Pluto. Now, one of the consequences of this curious atmosphere is that Mercury has a tail, and it's not any old tail. The tail is about 24 million kilometers long, because the solar wind and radiation pressure makes this Mercury vapor stream off the surface of Mercury like the tail of a comet. Just take a sip of tea. And so if you've got a Mercury filter, and some astronomers do, and that was how back in 1997 we discovered the Mercury, if you've got a sodium filter, that was how in 1997 we discovered the sodium tail of comet Hale-Bopp in La Palma. You can actually pick up the emission from sodium, and a number of amateur astronomers have picked up this sodium tail streaming out of the sunset when Mercury is visible. You don't see the full extent from Earth, but from space probes, you discover that it really extends almost out to the orbit of Venus. Quite astonishing object. Now, it seems to be a contradiction to have the surface vaporizing an atmosphere of sodium and yet ice at the poles. But again, very similar to the moon, Mercury Messenger, NASA's mission to Mercury, showed that there are quite extensive regions of permanent shadow at the poles. So you can see these at dark, particularly these crater floors. And when you combine them with yellow, which is the Arecibo radar mapping, sadly, Arecibo will not do any more radar mapping of the planets. You can see that the yellow patches, which are patches which reflect strongly radar signals from Earth, correspond largely with the floors of these craters. And it turns out that something very similar is happening on Mercury to happens on the moon. It's almost identical processes. Mercury here at the left, the moon at the right. Comets will impact both on Mercury and on the moon. When they impact, they vaporize, of course, and a large fraction of what comets have is water ice. So water ice vaporizes, provides the moon, provides Mercury with a temporary atmosphere. And some of this temporary atmosphere migrates to the poles and then refreezes. And the ice that refreezes in the bottoms of these craters stays there stable. It will not evaporate for hundreds of millions of years. And it goes accumulating and accumulating. And over the history of the solar system, both the North Pole of Mercury and the moon have accumulated millions of tons of ice. In fact, it's thought that probably there is even more ice at the poles of Mercury than there is at the poles of the moon. And there's a particular reason for this, and that is that Mercury, of all the planets, is the one that has its pole most exactly upright. Mercury has no seasons to speak of. The inclination of poles is only about 0.5 degrees. So once a region is in permanent shadow, it doesn't matter what you do, it stays in permanent shadow. And the estimation is that Mercury would have sufficient ice at the poles to sustain a manned, or I should say crewed base these days, for millions of years, probably, certainly thousands of years. There are other things that are very strange about Mercury as a planet. It has only 5.5%, so that's about a 20th of the mass of the Earth, but its density is almost exactly the same. Now, only the Earth has a very slightly higher density of all the planets. Why is this? Now, the reason why this is a mystery is that the Earth, the mass of the Earth, the gravity compresses the center of the Earth so that the density of the central core of the Earth is about 22, 23, if I remember rightly. So it's 4 times greater than the average density of the Earth. But Mercury, with its much lower mass, should not compress its center very much. It must be made of much more dense material. And in fact, when you compensate for this gravitational compression, you discover that Mercury is formed of material, on average, about 25% more dense than the Earth itself. So the average density of Mercury is not very much less than the density of iron, whereas the Earth's density is very much lower. It's much closer to the density of silicate rock, the rock that forms the crust of the Earth, than it is the density of iron. Why is this? Mercury has an amazing secret inside. It turns out that if you take a slice through Mercury and you take a slice through the Earth, you discover on Earth, of course, you've got the crust, you've got the upper and lower mantle, the liquid stuff that is coming out of the volcano in La Palma at the moment. And then when you go deeper down, you have the core made of iron. In Earth, a liquid outer core and a solid inner core. This is the part that is so dense, it's tremendously compressed by the mass on top of it. It turns out, though, that Mercury, the solid inner core, is actually slightly larger than the size of the solid inner core of Earth. And when you include the liquid core, it's more than 2/3, about 3/4 of the entire diameter of Mercury is just an iron core. And then there's a very thin mantle on top of that, and then a quite thick crust. Mercury is quite extraordinary that the proportion of iron core is enormous compared to the mantle and the crust on top of it. So why is this? There's been a huge amount of speculation as to why it is. Now, there are three basic hypotheses. Now, the first hypothesis that for many years was the most popular one, and it's still the most popular one, is that in the very distant past, very similar to what happened with the moon, a giant asteroid, probably one about 2% of the Earth's mass, crashed into Mercury. It smashed the original Mercury to pieces in this impact, and Mercury lost more than half its original mass. The heavier, denser rock that forms the core was held, but most of the lighter rocks of the mantle escaped into space and were lost completely to Mercury. This is a quite popular explanation. It's the most popular one for explaining the formation of the moon. Another theory that started to appear some years later is that maybe when Mercury started to form, it was largely vaporized. Now, the theory is that when the sun formed, it was much more luminous than it is today, and that the surface temperature on Mercury would have been at least 3,000 degrees centigrade. There are some estimates that suggest it may have been as high as 10,000 degrees centigrade, so much hotter than the surface of the sun today. It would have been comparable to the temperature of the surface of a star like Sirius. And so this theory goes that when Mercury was formed, the sun literally vaporized at least half the mass of the planet and just blew it into space. And Mercury only held on to the part that was most massive, most refractory, most resistant to this heat. So basically the iron core and a little bit of the exterior. And then there's a third theory that is not quite so extreme. It suggests that when Mercury was forming, it wasn't vaporized, it was simply that the solar wind blew away the lighter particles in the solar nebula and just left the heavier elements, the heavier particles, to accrete to form the disk of Mercury. Now, this is a relatively new theory, but the interesting thing is that when Mercury Messenger, the NASA probe, went to Mercury, it investigated and discovered that this theory could well be the correct one. Now, Mercury Messenger entered orbit in 2011, went into a very, very eccentric orbit. It's at perihelion, I suppose you would call it. It was only 200 kilometers high, and at its most distant point, it was more than 10,000 kilometers away. Now, this is an interesting orbit for mapping because it means you do get to see the whole of the planet. And in fact, Mercury Messenger completed just over 4,000 orbits, but it means that when you're closest, when you're lowest down, you're moving over the surface like a bat out of hell. So actually, Mercury Messenger was only able to take high resolution imaging for a very small part of its orbit, just a few hours of its orbit. And most of the time, it was actually getting distant views of the planet, which was good for other types of work. It was good for exploring the magnetic field of Mercury, but it wasn't so good for high resolution imaging. So Mercury Messenger, interestingly, found that the surface rocks of Mercury contained a lot more sulfur and potassium than they would have expected if there had been a giant impact or a large part of the mass of Mercury had been vaporized. Sulfur melts at a quite low temperature, lower than the surface temperature of Mercury. Potassium would be almost liquid at the temperature of the surface of Mercury. The fact that there is actually a fair amount of sulfur and potassium in the surface rocks suggests that Mercury was not formed in a giant impact, because those metals, those elements, would simply have volatilized and blown away into space. It suggests that it was actually that Mercury held on to the heavier components better than it held on to the very light ones. So that's the theory that the moment, even though it's not the most popular, looks to be in best agreement with the solution, with the observations. And then enter bepicolombo. Now, when bepicolombo first came along, and this was long before I joined ESA, it was proposed as a combined orbiter lander to orbit Mercury for 2.5 years and to land a small probe on the surface. Now, originally it was intended to launch in about 2009, and this later got delayed to 2014. So the original proposal, it would actually have arrived at Mercury 2 years before the NASA probe. Now, as we've got an image here of bepicolombo at the right, here's your starter for 10, fingers on buzzers, no conferring. What is odd about this probe?
It's got a trail as if it's got an engine running.
Right, that's one thing that's well spotted. That was not the one I was thinking of, Military Dave. Think that we are going somewhere very, very close to the sun.
Huge solar array.
It's got a huge solar array.
Exactly. You don't need a huge solar array so close to the sun. In fact, a huge solar array like that is a positive menace, because it will heat up massively close to the sun. There is a good reason for this. Now, it turns out that bepicolombo consists of 4 components. There's a main bus, and there are 2 sub-probes. And then you've got a little interstage in the middle. So first one, you've got the Mercury transfer module. This is the bus. You know, it's like the lorry that takes bepicolombo to Mercury, puts it into orbit. And as Dave so astutely pointed out, it does have a motor on it, which is solar electric. So it uses energy from the solar panels to heat xenon gas. And this is very, very low thrust, but it works consistently, constantly for months and months and months at a time. And this was actually one of the biggest problems that they had with the Mercury Messenger probe, that getting this solar electric propulsion to work was devilishly difficult. And that is the faint plume that Dave saw coming out of the bottom there. This motor is burning almost constantly during its flight. Then you've got Mercury Planetary Orbiter, which is the meat of the mission, or the meat in the sandwich, literally. That's the ESA orbiter. It's got 11 instruments on board, and it goes into a quite eccentric orbit, but much less eccentric than the NASA probe. It stays much closer to the surface of Mercury, so it's always got good resolution on the surface, and it's going to go into a polar orbit. So Mercury will rotate underneath it, and it will see the whole surface of the planet. And then inside the interstage, you've got the Mercury Magnetic Orbiter. This is a little Japanese orbiter. It also goes into a very, very eccentric orbit, even more eccentric than the NASA probe did, because it wants to dip right into the magnetic field of Mercury and study its variations. So it's an advantage for it actually to have a very eccentric orbit. It's got 10 instruments, most of them built by the Japanese, to study the magnetic field and its interactions. There's one instrument that is not supplied by Japan. So what we've got is a mission that is very complex, and in the end was delayed by 9 years. In fact, BEPI is the ultimate survivor, because it is the one occasion that the ESA Council, made out of the science ministers of all the member states, voted to cancel a mission. The vote, there were 17 members at the time, the vote went 11-6 to cancel the mission. Why was BEPI not cancelled? Because it needed a 2/3 majority. So BEPI survived by 1/3 of the vote. There were various reasons why there were trouble. Because it was overrunning because of the solar electric propulsion that was very difficult to develop. It was severely overweight. It went through various mass reduction exercises. There were huge cost overruns. And in fact, that has affected later missions that ESA is going to launch, because they've had their budgets squeezed to cope with these overruns. And in the end, BEPI is going to arrive 10.5 years later than Mercury Messenger, with a quite similar instrument package. And there's a real danger that NASA had done all the interesting science. However, there's also an opportunity there, because people have had a proper chance to analyze the Messenger results, and you can follow up and build on them. Sometimes it's not a complete advantage to be first. You have some time to digest what's been done, study it. What do we need to do to confirm these results? So one classic example is Mercury Messenger has given hints about the formation of Mercury. bepicolombo can now study in more detail and get the detailed observations needed to try and demonstrate which of those possible models is correct. And the other thing is that BEPI goes into a lower and much shorter period of orbit, which means it will be able to study more of the surface with high resolution. It really does take the scenic route to Mercury. It was launched in 2018, October 2018, in those happy pre-COVID days. And it has no less than 9 planetary encounters. First one with the Earth, then 2 with Venus. And here you see the reason why it needs those big solar panels, because the initial orbit went way outside the Earth's orbit, out to 1.2 astronomical units, and it needed our big solar panels to get enough power to run it at this distance from the sun. But when it's close to Mercury, those panels are a positive menace, and they get folded away. Another thing you'll see, each planetary encounter, the orbit gets a little bit smaller, and it slowly, very, very slowly, with each encounter, it gets closer and closer to the orbit of Mercury. Now, there's a particular reason for this, because to be able to orbit around Mercury, as it's not got a very powerful motor, it's got a small pack of thrusters, it has to reduce its relative velocity compared to Mercury almost to 0. It can't change the orbit very much to put it into orbit around Mercury. Now, the relative velocity between between bepicolombo and Mercury peaks at 100 kilometers per second. So in other words, BEPI is going 100 kilometers per second faster than Mercury. And this happens 3 times through next year in 2023. And it's very, very difficult to bleed away all this relative velocity. In fact, it's not until the 4th encounter with Mercury that there is a big braking, and finally the orbit starts to get much closer to that of Mercury, and the relative velocity goes down to just 20 kilometers per second, which is twice the escape velocity of Earth. It's still a big difference, but it becomes more manageable. So, as I've said, BEPI will go into distant polar orbit. First, it separates from the bus, and then the main probe and the magnetic orbiter separate, and over 3 months it trims its orbit. Now, Airbus have produced this lovely video, no publicity in it whatsoever, showing how this process is done. So I'm going to put So I wouldn't say this is dumbing down ESA science, but I found that video so fascinating. And you can see that actually the orbiter has very small solar panels, because the biggest single problem that BEPI has when it gets to Mercury is staying cool. It's a massive problem that they've got, and it has some very, very clever heat shielding to allow it to do that. Anyway, as we've seen, magnetic orbiter is the first one. That eccentric polar orbit's necessary so that it can sample the magnetic field at different places. Of the terrestrial planets, the Earth and Mercury are the only two that have global magnetic fields. The Moon and Mars have got local magnetic fields. Venus has some local magnetic field, but Mercury has a magnetic field that's about 1% of the strength of the Earth's magnetic field. And it's quite a mystery. We believe the Earth's magnetic field is quite largely due to the fact that we've got a large satellite that is stirring up the interior of the Earth and producing a dynamo effect. But nobody quite knows what it is that's causing this iron core, this huge iron core of Mercury, to produce a significant magnetic field. So that is one of the big things that Mercury Magnetic Orbiter is going to try and study. It's a 9.3-hour period. So I'll leave this as an exercise for the reader. So it's 730 days approximately in orbit around Mercury, around about two and a bit orbits per day. How many orbits will it do in the course of the mission? It's about, it turns out to be about 1900. You can check my math after the talk if you've got nothing better to do. So it will hopefully give us a lot of very good answers about what is going on with Mercury magnetic field, and how this magnetic field interacts with the solar wind and with the environment around Mercury. The biggest question is, why is it so strong? But also, how is it distributed around the planet? The planetary orbiter has very different requirements. It wants to have a much less eccentric orbit, because if you go into a very high eccentricity orbit, you spend almost all your orbit at the most distant point. I mean, that's a basic fact of orbital mechanics. A comet like Halley's Comet spends almost all its time out beyond the orbit of Saturn, very little of it inside the orbit of the Earth. So if you want to do detailed mapping of the surface, you want an orbit that is not too eccentric. So you're spending as much time as possible reasonably close in. It's got a 2.3 hour period. So it will make about double the number of orbits that Mercury Messenger did. So about 7,600. It will get a lot more very high resolution imaging than Mercury Messenger did. One of the interesting things about this is also because it does so many orbits, it will be able to do some extremely fancy gravity mapping of Mercury. Now, back in the 1960s, those of us who were old enough to remember the first missions to the moon, NASA was very, very perturbed by the discovery that the moon had mass concentrations, these big areas that were far denser, had far stronger gravity than the rest of the moon. And there was a real concern in NASA in the early 1960s, after they were discovered, that these could perturb the orbit of a manned capsule so much that it could put the astronauts in danger. Now we know that this is not a real issue, but Mercury Messenger discovered that Mercury also has two big mascons, one of them in the center of the Calores Basin, the big sea on Mercury, the big lava plain. So one of the jobs that Mercury Messenger did was to show where these mascons are, and now gives BEPI the opportunity to come out and study them and study how they relate to the topography, the surface relief of Mercury. So amongst other instruments, it's got a laser altimeter. Mercury Messenger also had one. It's got an accelerometer. It will measure very, very accurately the acceleration of the probe as it orbits around Mercury. And this will give it extremely accurate gravity maps that can be compared with the topographical maps. This will give us also a lot of interesting information about the internal structure of the planet, because with detailed enough mapping, you can work out the internal composition, where there's liquid, how much liquid there is, what fraction of the radius of the interior of the planet it occupies. BEPI will come up with hopefully some very detailed maps of the internal structure of the planet. And of course, another thing that it will do is study the ice at the poles. A polar orbit means that it will go over the poles of Mercury twice every orbit. Now, how do you map ice from space? It's actually very, very simple. That Mercury is bombarded by high energy radiation, both from cosmic rays, from the sun. There's proton bombardment, there's high energy ion bombardment from cosmic rays. And this produces neutrons emitted from the surface of the planet. It's a natural consequence. You hit the nucleus of an atom hard, and sometimes you knock out a neutron. But ice absorbs neutrons. It's a very, very effective absorber of neutrons. That's why you use water in nuclear reactors as a moderator, to absorb the neutrons, to control the nuclear reactor. So when you're flying over the poles of Mercury or the moon, and you see few neutrons coming from an area of the surface, that's a sure sign that there's ice under the surface. And by mapping the amount or the intensity of the neutrons coming from the surface, you can map very, very accurately the concentrations of ice. This was done with the moon by Lunar Prospector many years ago. And this has been largely confirmed by other probes afterwards. So BEPI has neutron measuring instruments that will do this. And of course, there is this whole question of the origin of Mercury. This is another of the fundamental questions that Mercury Messenger is going to try and solve. If it was modified by a giant impact, it should be missing volatile elements. They should have been blown off into space, scattered to, not to the four winds, but scattered on the solar wind. BEPI will be able to analyze the surface composition in great detail, has multiple instruments to do this. Among the instruments, it will map the surface spectroscopically. It will map in gamma rays, in X-rays. It will map in the infrared. It has filters on its visible cameras. And so not only will it take spectroscopy, which will reveal the lines that come from different elements in the surface of Mercury, it will also be able to take images in different filters, which will reveal the presence of different minerals on the moon. I've got an article, what I'm preparing for the BAA journal at the moment, which gives just an idea of how an amateur astronomer can do a lot of mineralogy prospection on the moon with just a CCD camera and images of the moon from their back garden, and it does not cost billions of dollars to do it. In fact, anybody can do mineral prospection on the moon and can actually do some quite useful research just using a CCD camera. BEPI, with its suite of very sophisticated cameras in the visible, the infrared, will be able to do a tremendous amount in this respect. Also has a high resolution stereo camera. So the images that we can expect to come from the surface of Mercury are going to be absolutely mind-blowing. So I've just put a couple of examples of images from Mercury Messenger. When BEPI produces its images, nobody's going to want to look at these. What about the atmosphere? As I said, Mercury has a very tenuous atmosphere with an extremely unusual composition. It's a planetary exosphere. So what that means, an exosphere is like the very outer layer of the Earth's atmosphere. It's technically called a collisionless gas. There's so little density that the atoms and molecules in the atmosphere don't collide with each other. Now, in the case of Mercury, the solar wind sweeps this exosphere away so efficiently that there is no possibility that it could ever become a proper atmosphere. In the case of the moon, actually, it's quite different. One of the strange side effects of having activity on the moon, industrial bases, large numbers of colonists, is that actually you could produce an artificial atmosphere from industrial research, literally atmospheric pollution, sufficiently strong that it could sweep the base of the exosphere off the surface of the moon and form a persistent atmosphere. You could actually form a significant lunar atmosphere that would be long duration. It would last for millions, possibly even hundreds of millions of years. That's because the exosphere gets electrically charged. And what it does is it directs the solar wind away from the surface of the moon. And it protects this tenuous atmosphere underneath, around above the surface, from the solar wind from being swept away. This doesn't happen with Mercury. Mercury's atmosphere is continuously being renewed. So the sodium, the potassium in the atmosphere, the oxygen, which comes from the breakup of minerals in the surface, this is being continuously renewed. As we saw, the sodium is being swept away permanently in that huge sodium tail. Sadly, there was one element of the mission that had to be sacrificed, and that was the lander. And this was largely for cost reasons, but also for weight reasons. And this is a real shame, because this would have been the most remarkable part of the mission. It's what would have made the bepicolombo mission so different to anything else that planned or has been done in the past. It would have been a very small lander that would have landed inside an airbag, roughly at 80 degrees latitude, 80 degrees north latitude, so in a fairly temperate region. The idea is that the airbag would have cocooned the probe inside, and that this, on landing, would have opened, revealing a small lander with its cameras to observe the surface. It would have placed this seismometer on the surface. It would have also put a small penetrator to dig into the surface, rather like the ExoMars 2022, it is now, probe, is going to have to dig into the surface of Mars. And it would have had more fascinating of all, or most fascinating of all, a micro rover, which would have been able to drive away from the lander and take images a little way away from the rover. The idea was that this would operate for a week on the surface of the planet. It is a desperate crying shame. It had to be cancelled. There was just no way that you could have taken the lander. And this was lost about 10 years before launch in the study phases. It was found to be completely impractical, but it's a pity. And when we go back to Mercury, undoubtedly, sooner or later, there will be a new lander, and hopefully a lander with a rover and a suite of instruments like Bepi. So if I'm not wrong, and breaking all the rules of my talks, as Guy will know, I'm always scheduled last at TA meetings because it's the threat of closing the hall and the last train of the night is the only thing that can get me to stop. I think that I have got to the end of this is my last slide. So even though Bepi probably won't get the publicity of ExoMars, it won't get the publicity of the sexy missions like Plato, Comet Interceptor, Rosetta. It will produce some absolutely amazing science. So I will not reveal who the gentleman in the photograph on the left is, but thanks for listening. Merry Christmas. And if there is anybody still there, maybe you have some questions.
Thank you, Mark. That was fascinating. And it seems you've probably set a couple of challenges for the Society. And I'm sure Mill Dave will be the first to challenge us to see who can get an image of Mercury's tail. If we
that's a relatively easy one, I think. I think the big problem's finding the sodium filter. If you can find a sodium filter, you know, that would be an amazing image.
Yeah. And the other thing, of course, is the mineral prospecting on the moon. So a couple of challenges there for the Society. So let's open up. If there's anybody, oh, Christy's got a hand up. I'm not sure if that's for applause or for a question. So
it's for a question. Thank you. That was really, really interesting. So I've got a question about the solar wind, which is continually kind of blasting off the atmosphere, which I'm going to make an assumption here is it continually replaced by the fact that the sun is burning off the minerals that are on the surface of Mercury? So if that's what's happening, is the planet diminishing because effectively the sun is vaporizing it?
That's exactly what's happening. It's happening very, very slowly indeed. But yes, you do see that sodium is vaporizing off, the oxygen is vaporizing off, and it's disappearing into space. But it's at a very, very slow rate. We're not talking about the sort of vaporizing that would have happened in the very early solar system on that second model that suggests that the sun literally burnt away half the mass of Mercury. It's not like a hot Jupiter one of these evaporating exoplanets that Military Dave was talking about before the meeting, if I remember rightly.
Oh, okay.
Plato is not interested in these, Military Dave. I mean, we regard them as a bit of an aberration. We're interested in Earth-like planets, but still.
Thank you.
Thank you, Christy. George, you've got your hand raised if you'd like to unmute yourself.
Yeah, firstly, thanks, great talk. I suppose a question, maybe an easy one, and that's dates. You know, when is the craft likely to be there, and when will we start to get some of the results through? And a second comment really is that you said the average density is not that much different from iron, but there are mass concentrations in certain parts of the planet. What sort of materials will be there which are denser than iron?
Mark's muted.
Yeah, sorry, I was trying to go back to the correct slide. I muted myself to stop any background noise that might cover up the question, and then couldn't find the control panel back. So let me just put up the slide again that shows the time scale for the mission. So there you have it. So
all right.
5th of December 2025, that's orbit insertion. However, if you remember, I said that it takes 3 months for all the separation of the different subprobes, the orbital trimming, and the orbiter probe itself is the last to go into orbit because it's got to bring down its orbit quite considerably to get into the target orbit around Mercury. So that takes about 3 months. However, during the time that it is coming down, they will be commissioning the cameras, commissioning the instruments, testing everything. And I think you can absolutely guarantee they will be very mad keen. There is a great deal of friendly rivalry between ESA and NASA. You can absolutely bet your bottom dollar that they will have some spectacular images and some interesting preliminary results as soon as they can get them out of the probe. And that will be long before it's in the final orbit, sometime around March, early March, mid-March of 2026.
Mark, how long is it due to last for? Obviously, they give an anticipated mission, which hopefully is extended. But what are their plans initially?
The planned duration is 1 year, and they're hoping for a 1 year mission extension. Now, the planned mission 1 year is simply because it's such a hostile environment. Mercury Messenger managed to survive 4 years, which is something of a miracle, because Bepi is going to be around about solar maximum. Their indications are that this is going to be a much higher solar maximum than the one that Mercury Messenger survived. And Messenger actually was there when maximum was declining. It was a very, very weak one. If the probe is still working after 1 year, you can guarantee they'll get their 1 year extension. They, like Mercury Messenger, though, they will run out of maneuvering fuel, and it would be not at all surprising if instruments start to fail, because if this solar maximum is like past ones, it will come in for the most god-awful bombardments in some of the solar storms. And it's an incredibly hostile environment to survive in.
John, you have a question?
Yes. Hi, Mark. I was wondering if the migration of planets, or the postulated migration of planets in the early solar system might have any bearing on one of the three theories of formation of Mercury?
That's a very interesting question. The migration of planets, I think, mainly affects the giant planets. So we've got a pretty good idea that Jupiter had a huge influence in the outer solar system, in the early history of the solar system, that Saturn, Uranus, and Neptune definitely migrated outwards. How much influence Jupiter would have had as close in to the sun as Mercury, I have my doubts. It might have had some, but I don't think it would have been able to change the orbit of Mercury as radically as all that.
Okay.
Of course, if Mercury had migrated, it would most likely migrate inwards, not outwards, and you would expect it to be formed of lighter elements more than the very heavy elements that you would expect extremely close to the sun. And I think Eric had a question as well. John, I don't know if that answers you. If it does, over to Derek.
Hi, Mark. I was quite interested in the observations of the neutrons to detect ice. I was just interested, how does one build a neutron detector since they are not charged particles?
That's a very good question. I'm not a particle physicist. The first neutron detectors were actually very, very simple ones. Crikey, I'm trying to think what the answer is. I think I'm going to have to pass on that question. You have got me there. The standard way of detecting neutrons that we did when I was at university was that you had something like a wax lens. Wax has got lots of hydrogen, carbon in it. And so when a neutron hits it, you sometimes knock out a proton from the wax. And that is one way of detecting neutrons. That's the way that Chadwick did it, for example. Originally, when he originally detected the neutron back in the 1930s, you just use the neutron bombardment to hit something charged out of another material. But I can't tell you specifically how they do it in these probes. You've got me there.
The only thing I can think of is ice, like they have in the detector at the South Pole, but you obviously don't want to carry that to Mercury.
No, it would probably evaporate before you got there. But certainly at university, we detected neutrons by using wax lenses. And that actually worked quite nicely.
I think modern detectors use a gas in a tube, and the neutrons collide with it, knock a proton out, and then you detect that ionization.
Yeah, that's the effect I was talking about. I guessed it was something like that, but my realm is more infrared than high energy and neutrons, so I didn't want to venture an answer without knowing.
Yes, I think, yeah. Well, I can think is catching you out was venturing into a field you're probably not so familiar with.
Anyway, we don't appear to have any further questions, or at least nobody has got their hand raised. So if anybody does have a question, please pipe up or raise your hand. But if not, can we show our appreciation for Mark for another splendid talk?
Yep. Brilliant. Thanks, Mark.
So what's the talk to Birmingham then, Mark?
You're muted, Mark.
Sorry, it's going to be an updated version of the talk I did to Basingstoke last year. So it's going to be about Betelgeuse.
Right. I was on their website and I couldn't find a way to join it.
Right, I hadn't. I can send you the link if you wish.
No, that's
Turned
fine.
on my camera, so I've
No.
turned it on now for the last few minutes.
No.
The bookshelves behind me are even more stacked than they used to be, because I discovered a reference in the that all the Apollo astronauts have now written at least ghosted autobiographies. So over the last few months, I've set out trying to collect every autobiography for every NASA Apollo astronaut. And I really am running out of bookshelf space, quite apart from other things that I've been collecting. It's
I'm going to set up a gravity anomaly there if you're not careful.
yeah, but the gravity anomaly, there was a question about that. I don't know if I answered it properly, that it is assumed that in the Imbrium Basin, for example, on the moon, that what the gravity anomaly is the remains of the asteroid that impacted with the moon, probably the iron nucleus of it. So one would assume, because there's this gravity anomaly in the center of the Calauris Basin, that there is one heck of a big asteroid hiding there under the surface as well.
I suppose that supports the original, your hypothesis that it was a collision way back that formed.
Yes, but the asteroid that would have formed the Calauris Basin, you're talking about, it's 1,500 kilometers diameter, higher impact velocity, so divide maybe by about 30 to get the diameter of the asteroid. You're talking about an asteroid maybe only 50 kilometers in diameter. That's a lot less than the sort of object you would need it to break Mercury completely.
Right.
Yeah.
Sorry, I do mute the microphone when I'm not speaking because my daughter's wandering around. And there is some background noise, so to try and avoid noise pollution.
That's fine. We're not suffering from any of that at the moment. So. Okay, so as I say, you've obviously got to get yourself ready for Birmingham. So we won't keep you any longer than need be, Mark. And it's really good to see you. And I think on behalf of the society,
Yeah, it's certainly good to see you again.
A really good Christmas and New Year, and hopefully when the pandemic's all over, we'll actually get to meet face to face.
Yeah, and I was hoping that this year I would actually be able to give the talk in person. And now I see people are talking not about third dose. I get mine on Boxing Day, which is working day here. They're talking about fourth doses, fifth doses. When will it ever end? It's, it's sad, but hopefully, please, Santa, if you're out there, I do miss my trip to Basingstoke, to Newbury, and the various other groups, Clanfield, in December. I hope very much next year I will be able to see you. And of course, TA meeting, which it must be 3 years since we had the last one, which, it's too long. No, it's not the same giving a talk virtually like this because you don't get the vibe from the audience. I just don't feel it. I don't feel people bouncing off me the way I do. And also, there are some societies which are very nice and they supply me with a mug of tea and gluten-free mince pie. Now that really was a nice touch. I think one year somebody even gave me a gluten-free Christmas pudding before the talk, trying to slow me down, I suspect.
We'll have to remember that for the future.
I have to say the hospitality I get is just absolutely overwhelming. You know, everybody has been wonderful. I think it's invidious to compare because you're all so different. Newbury, I think, won by a short head, but every society, the hospitality has been just fantastic. And the evenings chatting with Military Dave and his wife, you know, until their eyelids are drooping, and sort of, you know, I'm just wondering if they're going to throw me out. You know, that's just fantastic.
Of course, Newbury are famous for taking their guests out for a free talk meal.
Yeah, we're not going to hear the last of that now that George is taking that one on board. You can see him taking notes.
I won't mention it at our Christmas party.
It wasn't them with the mince pie or the Christmas pudding.
No.
That was probably Anne.
I have a weird anecdote about. I'm not sure if it was Newbury or Clanfield. Usually there's a Christmas raffle when I'm there, and I always buy some tickets to show willing. And at the BAA meeting, embarrassingly, 2 of my tickets came up. So, you know, I came back from that trip because I had the plaque from Basingstoke. I had 2 raffle tickets came up at the BAA meeting. It got a bit embarrassing. And one year I bought a string of tickets, may have been at Clanfield, and they announced the winner of the first prize. And I couldn't find my tickets. And so, you know, after a few minutes, they said, okay, well, obviously the person's not here. Let's draw out another number. It was only a few minutes later I discovered which pocket I put the tickets in, and I won the first prize there as well. So I'm glad that on that occasion I actually couldn't find the winning ticket. It's a bit embarrassing when you're a guest and you go away with the big prize.
I'm sure they would have forgiven you.
It's a good job you're working on the space mission and are also very lucky.
ESA, where I work, the way I explain it to visitors is it's like Disneyland for grown-ups. That's how it is. My second day at work was the day that Venus Express went into orbit around Venus. Big press event, special talks, presentations, fantastic. You know, I've been to so many of these events over the years. I've seen the launch of Herschel. I've seen spacewalk by the British astronaut. You know, so many of these things. It is an absolute privilege. It really is the most fantastic job in the world.
I hope you're writing your memoirs. Are you writing your memoirs?
No, not yet, but I thought the things that I've seen over the years, you know, I was there when Schumacher-Levy impacted on Jupiter. I saw Hale-Bopp from the observatory. I saw Hyakutake from the observatory. I've been present at so many of these amazing events. You know, I've seen Halley with the telescopes in La Palma. I've actually observed Mars and Saturn through the William Herschel telescope. Staff training night, somebody found an old brass eyepiece, put on the Naismith focus of the telescope. You imagine observing Saturn with several thousand magnification on a 4.2 meter telescope. It was better than the Voyager images. It was like being sat on the Voyager probe. Anyway, I promise you, I will finish the lunar mineral prospecting article. I'm collaborating with a Spanish amateur astronomer who's taken some lovely lunar photographs, and I hope I'll submit it over Christmas for the BAE journal, and we'll see when it comes out. I've got an article coming out in the journal this month, but this one, it's usually about a year and a bit from submission to publication. Anyway, with that, I think I really do have to love you and leave you and head over to Brum. Otherwise, Gary Poyner will not be impressed.
Well, Mark, many, many thanks once again, and we look forward to catching up with you and reading your article as soon as that's published.
Great stuff.
Okay, thanks very much, and thanks for the hospitality, and apologies for heading off quickly. And of course, when Gary does curse me, as he'll curse me in broad Brum, I probably won't understand a word of it.
So regards to Gary. But thanks very much indeed for taking the time this evening, and hopefully we can have you over again in a year's time. So thanks very
Okay,
much.
see you
Yeah,
next
cheers, Mark.
December, I hope. Bye.
Ta-ra.
Bye now.